Hello and welcome to this Breaking Defense webinar. It will run for about 60 minutes and is eligible for 1 CPE credit under the Business Management and Organization field of study. In order to receive the full credit, you must respond to 3 poll questions that will pop up on your screen over the next hour. By doing so, you will receive an email with the CPE certificate. This webinar is also interactive. If you have questions for our speakers, please submit them via the Q&A box at the bottom of your screen, and we will do our best to answer them during the webinar. Thanks for joining us, and we'll get started in just a couple seconds. Hello and welcome. I'm Barry Rosenberg, and thank you for joining us today for this webinar on offensive and defensive hypersonics. It's sponsored by TE Connectivity, and we appreciate their support. We have a 2-part webinar today. For the first 50 minutes or so, we'll talk with our military subject matter experts. Colonel Aaron Tucker, Chief of the High Speed Systems Division and Material Leader at the Air Force Research Lab, and Lieutenant General retired Daniel Karbler, Senior Advisor to the Missile Defense Project at the Center for Strategic and International Studies, and former Commanding General of the U.S. Army Space and Missile Defense Command and Joint Functional Component Command for Integrated Missile Defense. In our second part, we will then talk with Matthew Maclanis, Technical Fellow for Aerospace at TE Connectivity. So let's kick it off with our discussion of hypersonics with definitions of what we're talking about, particularly the different types of hypersonics. So, Aaron, why don't you kick it off by describing the difference between air-breathing and boost-guide hypersonics and the technical challenges they face, and then maybe we'll talk to the general, taking a larger holistic approach to talk about launch platforms. So can you kick it off for us, Aaron?
Sure, thanks for the opportunity, Barry. Look forward to describing how the air is moving through hypersonics. Generally, hypersonics is considered anything at or above Mach 5. In my high-speed systems division here in the Air Force Research Laboratory, we also consider high supersonic because there's, as you can imagine, there's a continuum between supersonic flight and hypersonic flight. Supersonic flight is broadly characterized with strong shock waves. Usually has a lot of drag of the shock waves. But when you imagine flying your aircraft or your missile through a blowtorch, and that pretty much describes the environment, the flight environment for hypersonic systems. You also asked about the difference between boost glide and air breathing. Boost glide, it uses all of its energy at the beginning, usually with a solid rocket motor. It accelerates the vehicle into that hypersonic flight regime, and then it separates out a glide body, and that glide body maneuvers by itself using gravity and the momentum imparted by the rocket motor in order to glide. It still maneuvers, often it has a maneuvering capability, but propulsion. Now, the difference on there in the hypersonic regime, able to provide thrust and propulsion in order to extend its range, capability, maneuvering capacity as well. So that's the big difference. But you also have to, of course, have a fuel system on an air breathing. And right now we're working with hydrocarbons. We were able to do that with the X-51 about 10 years ago in 2013. So that kind of gives an overview of where we're at with hypersonic systems.
Thank you. So Dan, how about you? How about a look at the hypersonic launch platforms and the differences and challenges that the Army faces with that particular bit of hardware?
Yeah, sure, Barry. Thanks very much. And I would say first that not just the Army, but all services have got challenges with countering hypersonic missiles as they come in. The biggest challenge that I see, the biggest difference between an ABT and a hypersonic is just the pure speed. As hypersonics come in, and as Aaron said, they're maneuvering, they're coming at an incredible rate of speed that, frankly, our interceptors might not be up for that particular threat. However, it's encouraging, though, that we have seen Ukrainian successes against the Kinzhal against the Russian Kinzhal missiles that got fired into Ukraine. So there is ability to counter that. Maybe some of the adversaries that are displaying right now are maybe a little bit oversold, but with that being said, we've still got to be able to take them on. Also, folks have said, if you can't see it, you can't shoot it. Hypersonics present a very, very difficult target for us to track, especially once they go into their glide phase after boosting. Pretty tough target to be able to see with terrestrial sensors. That's why Missile Defense Agency is working very hard in HBTSS to have a kind of birth-to-death sensor capability, or birth-to-death capability to track the missiles with sensors that are on orbit. And we've seen some preliminary success with that, some of the testing and work that we're doing. So in ABTs, just standard aircraft or cruise missiles, again, the speed, we don't worry about the speed too much. And then the last thing is just, and it goes back to the launch platforms, is, hypersonic is, if it's taken off from a tail or taken off from an aircraft, those just provide defense planners with additional challenges, because you have to know where these are being launched from, so that you can orient your systems in the proper direction in order to prepare your defense design.
Very good, thank you. Moving on to the next question, maybe we could start with you, Colonel. So the Air Force's HACM, which is an air breather, the Navy has the conventional prompt strike boost glide, and the Army has the long-range hypersonic weapon, I believe, which is also boost glide. So is there any coordination between the three programs? Are you coordinating? I'm assuming you are, but how are you coordinating with your counterparts at the Navy and the Army to kind of bring these weapons together in a sense, like right now, the Army, the Air Force, the Navy, they all have their own exercises like Project Convergence. There's a lot of talk that eventually they need to come together. I would imagine that might be the same with hypersonics as well. So what are your thoughts on that? Colonel Tucker? We might have briefly lost the Colonel while he was probably dialing in to try to improve his connection. So let me jump down to the third question, which I think this would be good for you, General. Excuse me. We hear a lot about ground-based mid-course defense, and we'll be talking about that in a little bit. I'm just wondering, how does defense against homeland hypersonic missile defense differ from homeland ballistic missile defense? Is that something that you could tell us a little bit about, General?
Yeah, sure could, Barry. Do you mind if I could just kind of throw a bone out for Aaron, since he wasn't up on the question that you had there? I would just like to touch on it a little bit from the operational perspective on the coordination between the programs. So not only is there acquisition coordination going on between the programs, but operational coordination, which is important when we're integrating fires. You mentioned Project Convergence, and really the Army's opportunity to bring its long-range hypersonic weapon into these different exercises. General Flynn, Charlie Flynn, the United States Army Pacific Commander, has really made it a point to make Army long-range fires integrated with the other joint fires. And you see a lot of really good work going on at the Combatant Commander. In this particular example, Indo-PACOM with the JFE, Joint Fires and Effect Cell, which really does the integration of all the different fires that are available to the Combatant Commander, of which now hypersonics among the three services is another arrow in his or her quiver. So I just wanted to touch base on, I did want to kind of touch base on that one before we got off of it.
That's fine. And we'll get to that in a second. Colonel, are you back? Okay. Let's move on to our next questions. So this is something here. I'm just trying to, in essence, a couple of these were specifically for for the Colonel, so I don't want to ask you a general question that you're not necessarily familiar with, such as one of the questions about attritable ISR and strike capabilities in hypersonics, though you probably are. Let me move down to another question here.
Hey, Barry, do you mind if we go back to the difference for Homeland Defense? Because that was the one that I
yeah, you're exactly right. Sorry, I just confused myself with moving the slides around. So that question's back up on the screen, General. Thank you.
Yeah, no worries at all. First, if I could, so it's really the Department of Defense's Homeland Hypersonic Missile Defense. And, obviously the Army as a service is going to do its role, but I would say, the Navy BMD and has already demonstrated some capability against hypersonic missiles. So we've got to make sure we give credit to all the different services. So some of the differences, and I'll infer from the question, ballistic missile defense, we're really talking about homeland defense against ICBM. And so they're very mature right now, right? So between the Colorado National Guard, Alaska National Guard, and the Colorado National Guard, those soldiers who man the missile sites, who man the command and control, they've been doing that for a long time. The National Guard has done a fantastic job doing that. We've tested it. We work very closely with the Missile Defense Agency operator and engineers, developer, hand in hand to make sure that the capabilities that to keep our country safe are being developed, not just from the technical side, but with the operator side in mind too. As we go forward into hypersonic missile defense, we have got to have that same mindset, an integrated mindset between the acquisition community and the operational community. Because if we don't, we just won't be successful, and there's just not enough resources, not enough budget or time to go around to have a bunch of different non-coordinated efforts going on.
Mm-hmm.
Some of the physics behind the differences is, first off, sensors. Again, sensors that detect ICBMs are going to be different than sensors that we need to be able to track hypersonics. It's a different threat, presents a different profile. But that's not to say that those sensing in that the surveillance picture that's being provided shouldn't be integrated. It absolutely has to be integrated at each command and control node that we have out there that's going to prosecute the flight or that's setting up the defense design. The interceptors are probably they're going to have to be different. Some ICBMs could maneuver, but they're not going to maneuver at the same rate, at the same speed or capabilities as a hypersonic missile. So different interceptors are also going to have to be procured and tested before we go on with our hypersonic missile defense. So just a couple of different things. One thing that I think that would stay the same though too is the command and control. We can't have separate command and control chains, whether it's a hypersonic missile or an ICBM coming in. We've got to make sure that NORTHCOM NORAD, is overall responsible for the C2, so that they can again direct the sensors and direct the operational intercepts that have to take place.
Mm-hmm. Very good. Thank you, General. So Aaron, I'll leave this question up here now. I know your specialty is mainly on the offensive side, but what are the differences between, you do get into some defense, is there an element of this question that you could respond to? Hey, Colonel, can you hear us?
Yeah, I think I heard the first part of your question. But the big difference is for us is it's often intelligence, surveillance, and reconnaissance being able and ability. As we move in doing research on burning down the risks associated with those areas, we need to be able to do thermal management, all the way up to a cruise Mach number in the hypersonic regime, or operate from a carrier aircraft and on a reusable type mission, or on an expendable type mission as well. That operates in that blowtorch we was referring before. That's very to operate a system repeatedly, operate a system with just the structure and the propulsion, as well as operating systems across the flight envelope as well. And those systems is what would characterize the reusable aircraft as either a strike or an ISR platform.
Sorry, folks. Colonel, let me come back to this question that the general responded to earlier. While you were working on your connection, the Air Force has HACM, the Navy has the conventional prompt strike, and the Army has long-range hypersonic weapon. So I know there's an organization, a group that you have where you coordinate. I wonder what the level of that coordination is eventually. And I was kind of thinking about things like Project Convergence and the Air Force's ABMS, and eventually those exercises have to come together, as I would imagine that hypersonics have to come together. Can you tell us a little bit about, what's the thinking between the services about bringing the programs together, if that's even something that they desire to do? Were you able to hear me, Colonel? All right, so let's move on to while the Colonel's working on his connection.
Hi, Barry. Aaron Tucker, how's this?
Oh, hey, Aaron. Did you hear my question?
I just heard that you were moving on, and I had to dial back in. So interested to hear. Is it the question on the screen there?
It is the question on the screen, and what I'll add to that, and General Karbler talked about this a little bit while you were working on your connection. The Army has PC, ABMS, and the Air Force. Just like those exercises need to come together amongst the services. I don't know, maybe is there a plan to bring the hypersonic capabilities of the various services together, or is the intention to have them keep going down their separate paths at one point? I know you have an organization, a group that you work with where you coordinate with the other services on hypersonics. Can you tell us a little bit about what's going on there?
Sure, happy to do that. So we work in some wargaming scenarios. I'll just share that primarily it's in support of Air Force Global Strike Command, and they have awareness through both STRATCOM and INDOPACOM about the joint fires coordinations that's necessary across the services in the way that they present their forces to the combatant commands. Because they're characterized by those different systems, air breathers and boost glide, they each have their different capabilities. So we're pleased to be able to complement the Air Force's air breathing systems with the Army and the Navy's boost glide systems.
Mm-hmm. Very good, thank you. So moving on. So this was something in our conversation earlier that I thought was very interesting, that the Air Force lead for R&D, test, and production recently talked about a shift to less mature technologies for reusable hypersonic platforms that will have both ISR and strike capabilities. I'm wondering, could you tell us about that kind of shift in philosophy to reusable hypersonic platforms. I was also interested in the ISR and strike capabilities. I didn't know if they were thinking of the missile would be performing an ISR mission on the way to the target, and then would be destroyed along with the strike. Can you tell us a little bit about that kind of reusable hypersonic platform thought that the Air Force is looking at?
Yeah, thanks for that opportunity as well. So I'll just share that with an expendable vehicle, with an expendable weapon, you have a limited magazine by definition, and it's based on the number of vehicles that you can mount on a carrier platform. But with the reusable platform, we can continue to hold those fixed high value and time sensitive targets at risk, and what we're characterizing as a responsive strike aircraft. Anytime you're dealing with large distances and getting inside a response time, high speed seems to be a way to affect that mission in particular. And being able to turn that vehicle on a short timeline as well is particularly important. And so that also lends itself to specific technology challenges as well. The power and thermal management, how do you continue to manage continue exposure to that the hypersonic environment, to that low towards the high heat and high shock waves? How do you operate across multi-Machs from Mach 0 to an operating Mach number and then back, and being able to turn that multiple times, and not only being able to turn it but understand the durability of that system. How do you appropriately model it using some digital models that have been validated with test and research data in order to understand the performance of the system? And metallic structures such as nickel, which withstand high heat very well. They also tend to require additional analysis. Similarly, if you apply like a carbon matrix composite material to a high-speed system, those aren't as well understood materials. And so what we'll have to do is we'll have to continue our understanding of how those systems respond, our understanding of how to digitally model the systems that are constructed of those materials, and then validate those models so that we can use those in an operational environment. And then the last technology gap that we'd be working on in a reusable system are mission systems. And that goes everything from landing gear and sensors to weapons and how to deploy the weapons as well. So working across the mission space and affecting our strike and intelligence, surveillance, and reconnaissance mission sets are pretty key for Air Force Research Laboratory.
Mm-hmm. Very good, thank you. Moving on to the next question, and this is something for both you, Dan, and Aaron. Hypersonics require sophisticated integration related to aerodynamics, structure, propulsion, mission systems, and payloads. And there's also a comparable set of technical challenges on defense, especially for launch platforms. So maybe can we start with you, Dan, to talk about the technical challenges on the defensive side?
Yeah, sure. We alluded to it a little, talked about it a little bit earlier, speed, the flight profile that the target presents are both a challenge for our existing sensors right now. And again, the good work that NGA is doing with HBTSS will help us to overcome some of that. I think that we really need to look at leveraging AI, and so AI might be overused a lot of times, but we should be able to build a database of missile performance out there, hypersonic missile performance out there, whether it's test, whether it's what the foreign industry is providing, and be able to create in that database enough information that will give operators a high confidence level of the threat that they're seeing, to be able to identify that and classify that threat, and then be able to provide the operational solution, the interceptor solution to counter that threat. And that's really it's a very technical solution to be able to get after that, but to the operator it would be transparent, and they would just, on their scope, they would have a track that said, okay, this is with 90% probability or 95% confidence level, this is what this track is, and therefore here's what the interceptor selection would be.
That's interesting. There's a lot associated with making that happen, General. All of the all domain command and control and the sharing of data across warfighting domains and security domains. What's a realistic kind of look from your point about how AI can actually make that happen? Is there some demonstrations going on now, and that's maybe something that Aaron can address as well. But that's also all wrapped up in JADC2 and all domain operations. Can you just address that briefly?
Yeah, sure. So, when I look at the question, right, and I always like to say physics gets a vote. You can't overcome physics. And so when you look at aerodynamics, structure, propulsion, mission systems, payloads, that there's information out there that we should be able to harvest that information, let AI kludge it together to give us what, again, a high confidence level of what we believe that target to be. And then, if JADC2 is the overarching C2 architecture or network that is enabling that information to flow, and again, across, domains and classification levels, what's important is that it has to get down to the operator so that, again, they can prosecute the engagement.
Very good. Thank you. Aaron, can you tackle this question, please, about some of the challenges on the offensive side?
Yep, appreciate that. So I talked briefly about the tech challenges and the tech gaps for power and thermal management, operating across the Mach numbers from Mach 0 to cruise or operating Mach condition, the challenges with building a structure that's durable to exposure to the hypersonic, the very challenging hypersonic environment, and then the mission systems that the general just alluded to as well. But one point that he brought in, which I thought was that we are taking very seriously, and something that's part of a research challenge as well, is mining the research data that are available and deliberately coordinating the generation of additional data that can validate those digital models. So I'll just say that hypersonic test data is very expensive, and it's actually some of the toughest ground and flight test data to collect. And so we're focusing on how to mine those data. He mentioned the AI mining AI techniques, and we're also interested in applying artificial intelligence and machine learning to mining some of these hypersonic test data sets so that we can align the validation data, the test data, into the digital design tools that we have to validate those tools in order to gain confidence in statistical confidence on the performance of those models as well. That's one of our enabling processes for going after and developing these high-speed systems. Digital material management is the term that we're using for the end-to-end lifecycle management and sustainment of systems that's backed by a validated digital model. There's even opportunity to advance the science of test. Researchers are working closely with testers in order to be able to more effectively collect flight and ground test data and roll those data deliberately and statistically into our design tools. We have to continue to increase our manufacturability of offensive systems as well. That goes durability is key, but being able to manufacture them rapidly and have a deep stockpile of expendable weapons, as well as a rapid production and an affordable cost of a reusable and responsive strike aircraft, I think is pretty key. And then the last one is a validated digital model can also be used to understand the military utility of these systems and be able to play it in some of those war games to which I was referring before. And not only play it in a war game, but also have confidence that that is something that maybe represents a reliable and a real system that's out there for the warfighter.
Very good, thank you. So let's stay with you, Colonel, and talk about the latest developments with HACM. Recently, we saw that the Air Force Secretary kind of put Arrow on the back burner. I don't know if it's because it accomplished all its goals or it just didn't seem like it had a path forward when HACM was under development as well. But could you tell us a little bit about what's going on with HACM?
So HACM continues to be broadly successful in its testing. We've seen a couple of good tests, and they've all been operational success or test successes. And I think that that's leading the program office to continue to work toward developing HACM and getting that system into production.
And to my earlier wondering about Arrow versus HACM, was there a specific reason that the Air Force is moving forward with HACM and not the other program?
So I'll just say that for hypersonic expendable systems in general, they tend to be they tend to not support two lines of effort, but we learn from each one. So you'll see lots of test systems that are up to learn a very specific objective, and then once we've settled on a design that's worth putting into production and continuing on across the life cycle, then that would be a good acquisition choice to just go with one.
Very good. Moving on, so Dan, similarly, can you tell us the latest about ground-based mid-course defense?
Yeah, sure. So first, as Missile Defense Agency is developing the next generation interceptor, they worked very, very closely with the 100th GMD Brigade soldiers. Those are the Alaska National Guard soldiers and Colorado National Guard soldiers who operate the GMD system. Again, I can't emphasize enough how important that is, so that the warfighter input, operator input, is part of the solution. It's not just a technical solution thrown over the transom to the operator who now has to figure out how to use it. And that cooperation, coordination has been going on for a long time between the Missile Defense Agency and the soldiers. And we continue to see that with next generation interceptor and the capabilities that MDA is developing in that missile. We don't just sit on our hands though with the current system. The service life extension program is ongoing with those missiles to make the current missiles that are in the ground, to keep them viable. Different software upgrades go into those missiles, and again, as the software engineers and the MDA engineers are working on it, they make sure that they get operator input into those, because that helps shape the tactics, techniques, and procedures, the TTPs the operators use, and it also has to reflect the NORTHCOM commander's requirements. And then probably the last thing is, the continued expansion of Missile Field 4 up there, where we're adding additional interceptors up at Fort Greely, Alaska, to, as the adversary continues to increase their numbers, Congress directed that we increase the missile field. So Missile Field 4 construction and additional interceptors, that's ongoing. That's very exciting in the missile defense world.
Very good, thank you. So we had one of the questions from our audience that I'll ask now. So we were just talking about GMD and NGI. A couple of our audience members have asked about directed energy lasers, electronic pulse weapons for hypersonic missile defense. What's going on in that area, General? Yeah, so if you remember airborne laser, the directed energy, the laser that came out of some port, that died a while ago. But the notion to be able to use directed energy to counter ballistic missiles has not gone away. And I know the Missile Defense Agency continues to look at different directed energy solutions to be able to get after that. And so, it's just it's no longer the chemical lasers that was kind of the challenge there with using airborne laser. Now the solid state laser is another. Yep, using up their magazines. Yeah, exactly. So now the newer technology that's coming on is promising. And again, we're not walking away from the ability to look at directed energy to help counter these ballistic missiles. Very good. Thank you. So the next question, test and evaluation has come up a couple times, and both of you on the offensive and defensive side have opinions on testing and evaluation. In our call earlier, we were talking about, how on the commercial world, like SpaceX, they get applauded for blowing up rockets and crashing them upon landing. until they eventually get it right. The DOD and government funders in Congress are not so happy when rockets blow up, I should say. And so it causes some problems in funding, frankly, for you. So can you address test and evaluation on both sides? Maybe Aaron, you could start first, and some of the challenges you face in test and evaluation.
Yeah, thanks for that question. I appreciate it. So testing is always about risk management, and early in the life cycle, the uncertainties are high, the confidence is low, but all data are good data, and that's a great thing about testing, especially when we have a plan to take those test data, ground and flight test data, and roll that into validating a digital model. It helps us accelerate the designs so that we can learn from the low confidence, high risk tests at the beginning and accelerate through the design life cycle. It's about managing risk with ranges. Ranges that we can use for hypersonic tests, especially on the expendable and reusable system, by definition have to be very large. So we have access to only a very few ranges that are associated with that size of weapon system and the speeds at which we operate. How do we continue to collect the telemetry data from flight systems? And for the ground test, there's only a couple of facilities that can accurately reproduce hypersonic flight conditions as well. The nice thing about ground test is that it's cheaper. It's usually an order of magnitude cheaper, and you can collect 10 times more data from a ground test as well. And again, it's the data rolling into validating those digital models. And as long as we can appropriately communicate the level of confidence and manage the risks of systems, I think I see a good path to a successful fielding of a hypersonic system.
Very good, thank you. How about you, Dan?
Yeah, I have a unique perspective. I used to be the Army Test and Evaluation Command commander, and our test infrastructure needs to be updated. It's incredibly archaic. Our telemetry, our sensors. I mean, you'd be amazed at the number of vacuum tubes that are still out there in White Sands Missile Range that we have to use in our systems just because we haven't refreshed them at the rate that we need to. And now when we have a weapon system like a hypersonic missile come in that requires exquisite tracking capability, great sensors, camera, optics that we just don't have right now. We really need to invest in that, and on the defensive side as well. My previous job, I was a senior commander for Kwajalein Atoll, and everybody saw the news of several months ago the wave that went through Roy Namur. Kwajalein Atoll is a strategic national asset where we conduct multitudes of missile testing, whether it's offensive or defensive missiles. Again, that infrastructure, not only is it old, but it faces just a very, very tough environment out in the Pacific Ocean. Corrosion, salt water. I mean, it's unrelenting. And so the Department of Defense really needs to get serious about improving and updating our test capabilities. And then we have to look at test ranges. Back in the 50s, we had a test range that spanned from White Sands Missile Range all the way up into Colorado. And it overflew Colorado, New Mexico, into White Sands Missile Range. It was very long, and that test corridor was used to test long-range weapons. We need to have the equivalent of that set up somewhere. I don't know where. Right now, we do it over water. You have to set up what's called the string of pearls for the telemetry and sensors, et cetera, to be able to get good test data. But we need to go find some real estate where we can put sensors on the ground and mine that test data that Aaron was talking about earlier. It's just a huge challenge. And then and Congress needs to help us out, and then Congress also and the services need to also be willing to accept failure as an acceptable outcome when you're doing tests. Because otherwise, if every program out there is gun shy about its test, either going to water down the test It's not going to make it as challenging because they don't want to fail the test because they don't want to lose their funding.
Yeah, I agree, General. I think that's why it's key to characterize a lot of these early tests as low confidence, high risk, and just go into it making that understanding. I liked your example of SpaceX, but back in the day, if you read the SpaceX history, they were on their last bits, and there was not a lot of confidence until they started flying and learning, and now they're the bright example of success. I mean, I see a path to that, but we are not in the high confidence area. We're in the low confidence, high risk area of the life cycle.
Mm-hmm. It's interesting. Elon Musk started out at Kwajalein Atoll. He was way far away from Prime. He had 1 million failures out at Kwaj, but he learned from them. He wasn't, it was away from prying eyes. It was away from, any kind of media scrutiny he'd have. He allowed himself to fail, and then he got better, and look where they are today.
Mm-hmm. Yeah, he was able to do that because he had access to the test ranges to which you're referring. Yeah, it's important to have those test ranges as national assets because you can't build them when you think you need them. You have to have them available to both the military and commercial development.
Mm-hmm. Good points there, and so all of those points fold into the next question. That there's been a lot of testing going on, so a lot of the low-hanging fruit has already been plucked, just like SpaceX crashing its early rockets. So what are the harder challenges of today? The things that maybe are a little bit more risky. Maybe I can't recall whether it was Dan or Aaron who said, I think it was you, Dan, where you said, test regimens are maybe not as complicated or as hard as they should be because of the concern about failure. So what are some of the harder challenges of today? Dan, can you start off on that?
Yeah, sure. I talked about it a little bit earlier, but I think just the physical geography that we need to test these weapons, give them true operational tests. I mean, you'll do all the lab work that you can, you do the developmental tests, but you've got to be able to do operational tests with operational realistic ranges in geography and distances. So that's the first part. Throw in then the requirement then to have updated telemetry, optics, to be able to harvest all that test information. And then the last thing is, the adversary is going to get a vote. So what are we doing to red team our testing and to throw countermeasures onto our capabilities so that we're not just developing a missile that's, as soon as it goes into adversary airspace is going to get, some sort of electronic warfare attack to knock it out of the sky. We've got to have the ability on our test ranges to replicate what the adversaries are going to do to our missiles.
Mm-hmm. Very good. And Dan, how about you? Some of the harder challenges. One of our earlier questions was about integration and the challenges associated with integration, all of the different parameters of the hypersonic weapons. What would you say are your hard challenges of today, looking at the tech from the side, from what it is that AFRL is working on?
Yeah, thanks for that. I agree that the integrated testing of systems is pretty key, and also having a plan to move rapidly from the basic research to applied research to technology demonstrations, and then getting into those integrated systems. And once we get to the integrated systems, now we can start to move from developmental or from research through developmental tests into operational tests where you're putting it into an operationally representative environment. The data set that collects that is key. The data set that you collect, that you gather at the beginning of the research phases into the developmental test phases informs the operational test. And you're able to then inform the warfighter about what are the capabilities, what are the risks of the systems, and having a clear-eyed view of the benefits and risks of any weapon system, I think, is pretty key. And that's why we have that continuum of test from research to developmental test to operational test. And then the last part is, I think that the general already mentioned it, is collecting these large data sets with telemetry across large expanses of terrain or water under our ranges. I mentioned the string of pearls. I know that we're trying to replicate that with airborne assets, with unmanned especially, so Global Hawks, Predators, that type of thing. That will allow us to collect much larger data sets. The data will be able to get rolled in to validate our digital models and accelerate our ability to design and develop hypersonic systems.
Mm-hmm. Very good.
Hey,
Thank you. Yeah, please. Go ahead.
Another thing I have to is the bureaucracy behind test. There's a thing called the Test Evaluation Master Plan, the TEMP, and that is a bureaucratic document that takes 2 years to get staffed and approved and requires about 20 signatures. And that is no way to move fast in a world where we have to move fast. So I just want to throw that out there too. We've got to overcome our test bureaucracy so that the acquisition and the operational communities can move out with capabilities.
Mm-hmm. Very good. So Dan, you set yourself up for the next question. So the Missile Defense Review comes out, it seems like annually, maybe every other year. It sounds like you might have some recommendations for the next Missile Defense Review. What would some of those be?
Yeah, I think, right now the current policy is that the U.S. ground-based mid-course defense is designed against North Korea and Iran and rogue nations. Given where hypersonics are coming from and the adversaries that they're coming from, I think the Missile Defense Review is going to have to open up its aperture, and it is going to have to it's going to have to call a spade and identify Russia and China. And I know folks get very concerned that that'll put us into an arms race, but I also don't think that it's responsible for us to sit on our hands and not have capabilities to defeat hypersonic missiles as they come in. So I think the MDR has to specifically call out Russia and China as threats that we are building a hypersonic defense against. And then the second part would be, and this is more in Aaron's lane because it's the offensive side, is that the MDR, because it's truly integrated missile defense, it includes attack operations. And we've got to be a bit more forceful in our Missile Defense Review in terms of how we will use attack operations. Potentially, we use them preemptively so that we're not taking the first 2 or 3 shots. Instead, we're going to use these hypersonic weapons we're developing to strike first.
Excellent. So, Aaron, do you have anything you want to add to that regarding the attack operations that the Missile Defense Review addresses and what you may be interested in seeing in the MDR as it relates to the work that AFRL does?
Yeah, so AFRL is in an important part of the research area, and hypersonics is an important part of the AFRL portfolio as well. I would say that there's still some discoveries to be made. I think that those discoveries can contribute to the Missile Defense Review. We design, we develop, we engineer these future systems, and we can collaborate. We can work with the MDA and form the Missile Defense Review because our place in the technology development ecosystem is to be the subject matter experts on hypersonics. And I think that we have some important contributions to that review on the technical side.
Okay, very good. Thank you. Last thing I'll ask you is how offensive and defensive hypersonic developers can work together through things like red teaming. It was mentioned earlier. I think Dan said, the last thing we want is to have a missile entering enemy airspace and then just knock down with EW. So how can offense and defense work together through things like red teaming and other things that I haven't thought about? Can you tell us a little bit about that? Can you start, Aaron, please?
Yes, I think red teaming is important because it allows us to identify some of those vulnerabilities that you have in your question there. But understanding even just the gaps in knowledge will help us identify the areas of research that we need to be targeting our relatively limited resources. Hypersonics has been on several peaks over the last 50 or 60 years, starting with X-15, going into shuttle, NASP, X-51, and now our current work on fielding a capability for the warfighter is really what's focusing our research. And because AFRL has the ability to go from basic research and discovery to design, developing, and engineering new systems. I think that that's an important voice in the collaboration with hypersonic system developers.
Very good, thank you. How about you, Dan?
Yeah, really quickly, really have benefited a lot from the move of the Air Defense School when it moved from Fort Bliss, Texas up to Fort Sill, Oklahoma, which is the home of the field artillery. So the fires community, which is offensive and defensive fires, has come under one roof up at Fort Sill. And so since 2009, we have been learning from each other, vulnerabilities, tactics, techniques, and procedures. Our Army capabilities managers share information, and then we push all that down to the operational force. So you will see fires professionals really snap linked in with each other, offensive, defensive, defense design, targeting, and it's really, the last, since we came together, it was a little rough at first, but now the fires professional and fires community, you almost can take a field artillery officer and put him in an air defense position, or air defense officer put him in a field artillery position because of the skill sets that we're sharing now. So I would use Fort Sill as kind of a model for how we bring offensive and defensive together.
Mm-hmm. Excellent. So that was our last question for the panel before we move on to our next technical expert in hypersonics. But first, I'd like to thank Colonel Aaron Tucker from FRL and General Daniel Karbler from CSIS for joining us today. It was a great discussion, gentlemen, and thank you so much.
You're welcome, Barry. Thank you.
All right, thanks, guys. So now we're going to continue our conversation with Matthew Michelanis from TE Connectivity. Matt is Technical Fellow and Global Leader of Engineering for TE's Aerospace Defense and Marine Business Unit. Thanks for joining us, Matt, and we've heard some interesting things so far during the webinar.
Yeah, thanks, Barry. It's great to be here. Thanks for having us.
So let's build on what we've heard so far with a few questions for you. Let me move on with the slides. So connectivity is required for offensive and defensive hypersonics, especially in rugged fashion, to process and communicate sensor data. We've kind of been hearing a lot of that throughout the entire conversation. So can you describe this hypersonic challenge of operating, processing, and communicating in rugged environments?
Yeah, this is quite a realm of, I would say, opportunity here in this arena. When you think about all the domains that connectivity needs to work reliably in, and that's what TE is good at. So we're enabling reliable connectivity to keep us safe, to keep us productive for a sustainable future. And, part of that is working in areas like the standards that are behind the sensors. And one of the main ones that a lot of the groups are working with is called SOSA, and it stands for Sensor Open System Architecture. So what that does is that enables the community to have a dialogue about the types of sensors, the requirements behind them, and sensor is a very broad term. And, you think about detection, we talked about that in the first segment, talked about navigation, targeting, and the whole spectrum of how you connect. And sometimes that's the photonic spectrum where you're enabling fiber optics. It's obviously in these environments, a lot of wireless. So it's the RF spectrum in there. And then you heard a lot about data. And data is about high-speed digital processing. So at every level, that's where TE can be involved with this in connecting these subsystems.
Mm-hmm. Very good, thank you. Next question was how TE Connectivity handles system testing, not necessarily just at the component level, but whole system architecture testing.
Yeah, so when you think about these systems and where they have to operate, and again, thinking about offense, defense, and detection, so many of the sensors could be in outer space. And when we work with customers, about requirements, they often will approach us about a component, and that might be a wire, it might be a connector, it might be fiber optic, it could be, any type of component thing like that. And the discussion we need to have is really about the architecture and the subsystems being connected. And when you think about data, acquiring it, whether it's through maybe GPS, so obviously outer space and other types of sensors, whether they're visual, thermal, RF, that information has to be sent somewhere and communicated. And when it gets sent somewhere and then needs to be processed, and when it gets processed, it then needs to be displayed to someone. So we have all kinds of different connectivity happening. It could be electro-optic conversion, it could be the RF, so analog to digital conversion. And at TE Connectivity, we attempt to make that a seamless transition through our connectivity. So understanding how temperature affects it. So in hypersonic, obviously, we have sensors in the front of a flying object. Ever see something entering our atmosphere? It's very, very hot environments, and that's where the sensors are, that's where the antennas are, that's where the control surfaces are. So we need to enable things like health monitoring and not just of the vehicle, but just all the connectivity involved with that in the communication. So when we work with our customers and talk about architecture, we need to understand the building blocks, how things are being connected together, and make sure it's done properly, reliably, and we don't have a bottleneck in that information flow.
Excellent, thank you. Last thing I wanted to ask you, Matt. So we're all aware of missiles and silos and the years and years that they stay underground and in other sort of launchers as well. So how do you ensure that these systems stay viable over time so the communications works when needed?
Yeah, I would say the great thing about TE Connectivity is we have decades of experience and the science behind our products. So it's in many cases the materials that we're using to put on our cables, and we have a legacy that goes back to the Apollo missions, where we were the cable connector company that enabled that video feed going down to as the men first got on, took the first steps onto the moon. And when you think about that legacy of reliable connectivity, and we're still used in, the satellite systems, the connectors, the types of wiring that's connecting the solar panels and all those things. So when we look at some of these systems, many of them are, I would say, obviously a deterrent to being used, but when they sit and wait in persistent surveillance mode, and being ready, they have to work when they're needed. And sometimes these environments are harsh environments, maybe underground or airborne or in marine environments where there's salt corrosion and things like that. So we have to really do our due diligence in the compatibility of materials and the stability of materials over time. We don't want to have degradation modes happening while the units are waiting to be put into service. So that's where we do testing, long-term testing, understanding the failure modes, the contact physics, and the modes of reliability that we're enabling.
Excellent. Interesting stuff there. So thank you, Matt, for adding to this discussion today. So we've reached our hour webinar time limit, and so that's it for today. And on behalf of Breaking Defense, thanks to everyone who joined us. Goodbye.